I'd like to welcome you all to the second webinar in our series on graphene and the 2D experimental pilot line. It's co-hosted by the Euro practice and the Graphene Flagship's 2D experimental pilot line, or 2D-EPL. I'm Rebecca Waters, the Graphene Flagship's head of dissemination. If you missed the first webinar in this series and want to learn more about Euro practice, the 2D-EPL, or what makes wafer scale integration of graphene so interesting, you can find the webinar on Euro practice's YouTube channel. And we will actually have one additional webinar, as you see on the slide, on June 2nd, looking into the future of the 2D-EPL's multi-project wafer runs and how the project will evolve over the next few years. But today, Gordon Rinke is with us to dive deeper into the topic with a discussion on the 2D-EPL's upcoming multi-project wafer run. Gordon Rinke is the project manager for the 2D-EPL and is deputy head of the graphene electronics group at AMO. Dr. Gordon Rinke obtained his PhD in material science from the EPFL Lausanne, Switzerland in 2013. And after spending over 6 years in industry for a semiconductor tool manufacturer as lead process engineer, he joined AMO in Aachen, Germany in 2021 as project manager for the 2D-EPL project and became the deputy for the graphene electronics group. His background is on the nanostructure growth and fabrication of organic and inorganic materials, as well as process development and optimization. So without further ado, I turn the floor over to Gordon.
Yeah, thank you for this nice introduction, Rebecca. And I would like now to continue here the series of this webinar on Euro practice by telling you a little bit more about the first MPW run we are providing here within the 2D-EPL project by giving you some key specifications on these devices. And I would like to outline this talk in the following one, and I would like to start, for those of you who don't know AMO in detail, to give here a short introduction. And then I would continue to give you more background information on the 2D experimental pilot line, where these MPW runs are all processed or where these are located. And then I would like to show you some general fabrication steps of graphene devices. I would like to pick out there some important things before I then come to the details of this first multi-project wafer run by describing the baseline process, the die design, timeline, and how you can participate. So to start off, I'm starting now to introduce AMO, and AMO is actually the abbreviation for Applied Micro and Optoelectronics. It's a small non-profit nanotechnology and SME with a mission to close the gap between in university research and industrial application. And we are located here in Aachen, close to the border to the Netherlands and to Belgium. And this we see us as pathfinder for innovative technologies and dealing with 2D materials research here in a global manner. We were founded in 1993, and at the moment we are more than 60 staff members involved in more than 40 funded R&D projects with more than 150 R&D partners all over the world. And our technology we are applying here is based mainly in silicon technology, nanofabrication, and we are essentially looking for the integration of new materials. This was high K and metal gates materials in the past, developed now to graphene and 2D materials, but also on perovskite, and then we are also active in plasmonics. And all of these are applied for applications in the field of nanoelectronic, nanophotonics, and integrated sensors. In order to do this, we have a clean room available, which is equipped with the standard technology you need for semiconductor fabrication. This is on one side, of course, the lithography. Here we have different things available like electron, optical, interference lithography, but also nano imprint. We do the pattern transfer here by ICP or real tools. And of course, we also do deposition of various materials by applying different techniques like evaporation, sputtering, ALD, and CVD. Furthermore, we also have wet processing available to do further lithography or etching processes. And of course, metrology also plays an important role to analyze and characterize the things we do. And there we have, for example, Raman, photoluminescence, electrical measurements, and electron microscopy measurements available. But also with our startups and spin-offs, Protemics and Amatronics, we have also connections to do terahertz conductivity or transients recordings. At the moment, our current interest is here in scalable 2D materials and technology, and this is not only graphene, but also semiconductors like MOS2, and especially the integration of 2D and 3D hybrid structures. And this is in the fields of mechanical or electrical systems and sensors, like here this is a pressure sensor, but also in the field of optoelectronics, like a graphene photodetector here. Electronics, this is an example for RF graphene transistor, but also for flexible electronics. And here are some examples for a photodetector or Hall detector on these substrates shown. And this interest here is mainly based on the fact that 2D materials can improve the functionality of CMOS technology in many different fields. And this is here a graph which already showed my colleague in the last webinar, showing the different fields of 2D materials. The orange color here representing graphene, whereas the green one is more for TDMCs. So there is a huge branch of things possible. And if you look on this other graph here, this shows that where 2D materials have the market opportunities in the next years, and there are different keys, like different technologies or devices, like functional devices in optoelectronics or in logic devices, and there are a few spots where the market opportunity is very high. So the forecast of these technology seems to be massive in the coming years, and what is missing here a little bit is then the integration of those materials on a larger basis. And to pave this way into this wafer scale processing or this mass production of graphene and 2D devices, the 2D-EPL project has recently started to build here some kind of roadblock or wave map or roadmap in order to get there. And these 2D experimental pilot line project, I would like to introduce to you now. So this is has the target to bring 2D materials from the lab to the fab, which means essentially to bring the devices from the chip scale to the wafer scale. In this case here, in the wafer sizes of 200 millimeter and 300 millimeter in particular, and in the meantime also making these 2D materials compatible with the standards in the semiconductor industry. This means by the development of critical tools, but also of chemicals and materials in order to achieve all the targets here. And by doing this, the project also has the aim here to establish European ecosystems for the integration of 2D materials. In parallel to that, there's also a foundry service introduced in order to give open access to these functionalities of these 2D materials, and also to support the establishment here of a new industry providing these functionalities of these materials. The project is part of the Graphene flagship, started 2 years ago, 1.5 years ago, in October 2020, has a duration of 4 years and is funded by 20 million. The approach of these projects I try to display here a little bit. So it's based on 2 pillars. The one side is the prototyping from the day one, essentially, by giving access to the existing technologies, in particular on the 200 millimeter platform. And here, this is also the pillar where mainly the MPW runs will be provided. And in the second pillar, this is the place where the development of the tools, but also of the modules and platforms is taking place on the 200 millimeter platform, but also on the 300 millimeter platform. And what you see here indicated by these arrows is that, of course, we try to always bring the state of the art into these MPW runs at each state in order to really provide the latest research and knowledge here to the public. How is it organized? So the project consists of 11 partners, all distributed around Europe, ranging from tool vendors and companies up to research institutes. And of course, the development of the tools and materials is provided by the tool companies and material companies like SÜSS, Extron, Microsys, Oxford, or Graphenia, whereas the development of the modules and platforms are done by the research institute. And this is here in this case VTT, IMEC, AMO, and IHP. And the multi-project wafer runs, where these pilot lines are located, is taking place at VTT, IMEC, and AMO. And these are also here the 3 locations where the different multi-project wafer runs will be carried out. The runs itself are displayed here again on this slide. So as if you have seen already, they will be presented in a subsequent way. And all of these runs have different targets, whereas the first 2 ones are dedicated to graphene sensors. The third one additionally includes electronic devices. And the 4th one will be provided on CMOS wafers. Whereas the 5th one here is not dealing with graphene, but with TMDCs and TMDC-based transistors. And this will be the last one within this project. And you can see here also, so the first one is provided by AMO, whereas the run 2 and 4 by VTT, and the last one then is mentioned by IMEC. Before I come now to the details of our first run, I would like to talk about the general fabrication steps of graphene devices. We have seen this already in the last webinar of my colleague a little bit, that the procedure is like this, that you have a graphene growth on a separate substrate, and then you do a transfer, a patterning, a contacting, and then an encapsulation. So this is roughly the scheme which you follow. And I would like to talk about a little bit on these 3 things here in the middle. So the transfer and the patterning and the contact thing of the graphene, as these are some important steps during the fabrication. The transfer of 2D materials is necessary as they are mostly grown on different substrates due to high temperature or as they are catalytic surfaces needed. And these are not always compatible with the targeted wafer, where you have to process in CMOS conditions maybe. So there is a need for transferring these materials. And 2 methods I have displayed here on this slide. The first one, the so-called wet transfer, is called like this because it's mainly done in solution. And you start here with your graphene, which is grown in this case on a copper foil. You coat it with a PMMA coating, and then you remove the substrate, the copper foil here, by etching it in solution, and then afterwards rinsing it again. And so you end up with the PMMA layer and the graphene in a wet solution, which you then put on a target substrate wafer. And after drying and removing the resist, you end up with the graphene on the target wafer. The other approach, the so-called dry transfer, is using, it starts also from your material on a different substrate, but in order to transfer it to the target substrate, it uses force and heat in order to bring the 2D material onto the target substrate. And this can be also done here with an additional adhesive layer in order to bring the forces then later to the substrate in order to remove mechanically the growth substrate. And then you end up here with the graphene layer on the target substrate. A so-called semi-dry transfer would be if you remove the copper surface, in this case also with a wet etching solution, then you speak of a semi-dry method. The patterning at the nanoscale. So what you would be then the following thing. So what you have then is your graphene on a completely covered wafer. And in order now to prepare your structures of graphene in the desired shapes and designs, you have to structure it. And probably most of you is familiar with the patterning at this stage in the micro and nano scale by using photolithography. So you start with a resist here, using a photo mask with your desired structure, exposure it to light, and then develop the structures. And through these structures, then they can be used in order to deposit certain different materials on top of this wafer. And after the lift off, you have these structures with a certain material, or you use these structures in order to use them for etching. And this would be the way here, for example, if you want to structure graphene in a certain way. So you etch away the graphene at the positions you don't want to have it. And of course, this patterning, you just don't apply for graphene, but also for the contacts and everything else you need on your chip in order to fabricate the functional design devices. And this you have to repeat layer by layer. After having now the graphene in the shape you want to have it, you have to contact the graphene or the 2D materials, and there are different types available to do this. And of course, these ways of doing it can have an important impact, as it has an influence on the contact resistance. Also, the contact resistance is a result of the contact metal, so choosing here the right metal is also very crucial in order to improve the device performance. But the contact type is something which I showed here. So you have, for example, the option to fabricate contacts on top of the graphene layer, then it's this top contact. But you can do it also the other way around by fabricating first the contacts on the bottom and then transfer the graphene layer on top of it. And if you do a mixed way of that, so that you have the bottom and the top contact, you speak of a so-called sandwich contact. And the fourth type you can contact graphene here is by using an edge contact. This is a little bit different than compared to the other ones, as you are here directly try to connect the graphene to the edge of the at the edge, as there are additional bonds present which support the charge injection here at the area. And in comparison to the surface of graphene, this is an improvement, as there are no free dangling bonds available, which can improve the charge injection here. So there are different types of contacting available. And this brings me now to our run directly. So what we have chosen here is the following. We have a GFET here with a top and bottom contact, with a graphene layer on top of a local backgate and with an encapsulation. The whole device is on a silicon oxide substrate, and we will fabricate this on a 200 millimeter wafer, which will be then diced or sized in 1x1 sizes for the individual chips. The key parameters of this device are summarized here quickly. So we have a graphene mobility above 1000 square centimeters per volt second, and the average contact resistance here in the range of 2 kilo ohms. And we have the direct point here below 50 volts, and and a safe gate to source voltage range in plus minus 50 volts. The process of these devices is shown roughly in this sketch here. So first there will be the backgate and the contacts be deposited, then the dielectric. The graphene is then transferred before then the contacts and the encapsulation will be done. And optionally, we have also the possibility here to open the encapsulation on top of the graphene layer. The layer thicknesses of these devices are summarized here in this table. So we have here in total 6 layers, as mentioned, started with a gated dielectric or backgate contact with a thickness of 40 nanometers, and we use here palladium. It's followed then by a gate dielectric of aluminum oxide with a thickness of 75 nanometer. And optional, you can of course leave this gate contact away. Then you still would have the possibility to gate your device through the global silicon substrate. After that, the graphene layer, which we provide here, is a single layer. This is grown on the 200 by 200 meter copper foil by our partner Graphenea, who will also do the graphene transfer in this case with the semi-dry method. And after the transfer is done on our substrate, the graphene patterning and all the following steps will be done again in our lab. In particular, will be done by our lab. As mentioned, so the contact here of the graphene layer will be done by a sandwich contact with palladium metals in the thicknesses from 30 nanometers for the bottom contact and 40 on the top. And then afterwards, the encapsulation is again done by aluminum oxide with a thickness of 80 nanometer. Or also, we have also the possibility to use here SU8 with 7 micrometer thicknesses. For both of these types, we are offering to open the encapsulation here on top of the graphene in order to have access also to the graphene device for further functionalization, for example. And what you can do with these samples, just as application examples, I would like to show you now on 3 following slides, which also already have been shown by my colleague in the last presentation in a little bit more detail. But for example, the encapsulated device can be used, for example, as a Hall sensor, where you have your graphene here structured in this cross here. And then by applying a voltage across this bar and measuring the Hall voltage in the magnetic field, you are able to detect the magnetic field or the changes here. An example for having these devices with an opening on top of the graphene layer is shown here. So this allows you to functionalize the graphene, for example, with a molecule which is sensitive to the NH3. And in this way, you have a conductance change, very selective for this special molecule. And so you have here can realize a gas sensor with this device. Another application for having these devices with an opening on top of the graphene is here shown for a photo detector, where you now can functionalize the surface with graphene quantum dots. And here these quantum dots, they generate electron hole pairs which are charged and then leads to a charge transfer into the graphene. And by this, you can detect the light by measuring a different resistance in the dark or in the illumination state. So this is also a method then here to increase the gain and the responsivity of graphene to light. And all these designs can be realized on our MPW run. What we are offering here is that you have the whole die available for your individual design of your devices. We will provide you here this GDS file, a template already, where you have here almost the whole size available. In this example here, we have also included some of our reference devices like this TLMM structure, 4-point measurement or Hall bar, which can be used as a reference for further modification, or if you like, you can also take them directly, but you can also completely erase them from these and build your own design and your own devices as you require them. Regarding the design rule, there's essentially only this single one, which means that the design has to be larger, or the distance has to be larger than 5 micrometer. This is due to the fact that we are using here optical lithography, contact lithography, and which represents here the physical limits of this process. During the fabrication, we will of course have a look at the quality, so that it's completely transparent what has happened during the fabrication. This will start with Raman after the transfer, for example, at different positions, so that we have an overview how the graphene quality here is roughly distributed over the wafer. We will do, of course, also optical inspection after each step to see if there are any contaminations or things not going the way as we wanted. And then in the end, after the wafer has been processed completely, we are planning to do electrical characterization with our reference devices, which we are planning to have in between the dies, so not on the dies itself, in order to get an overview how, for example, the mobility is distributed across the wafer, so that every customer then can also expect the quality of their dies in a certain way. And all this data, of course, will be provided so that we are here also completely transparent. Which brings me to the timeline and the costs. So the call for this MPW run has started in 1st of February. And this call is open until the end of June. Then we will use the time here to collect all the different designs into one wafer or 2 wafers, prepare the mask for them, and then start the MPW run will start in the 1st of September and lead until the end of October. We offer these services here for a set price for 4 dies for 1,300 euros. So with an identical design, and any die more, we would ask for additional 250 euros. And we are also providing a discount here of 24% for customers from countries participating in the Horizon 2020 framework. And if you would like to participate, I depicted here again the application process. So you can applicate here for this MPW via our web page, the 2D-EPL pilot line. You will find there a form, an application form, where you have to type in your details, your name, email address in particular, and then submit the form. You will directly receive a confirmation email that this formula has worked, and we will get in contact to you again in order to, in one side, to send you the NDA, but on the other side also to schedule a meeting in order to discuss your preferences for the run and for the meeting and the design. And after that meeting, we will provide you this GDS document where you can draw your designs, and again a document where all this information which I just shown here in those slides are available again. And then we will be in the design phase. We will get in contact again if there are any further questions until you have fixed your design, and we can continue with the order and then fabricating your devices in this time frame here. Yeah, and this brings me already to the end of the talk. So I hope I could introduce you to AMO and the 2D-EPL project with our first MPW run, which is dedicated for sensors. I hope I could show you a little bit insight into fabrication of graphene devices and the basis or the details of our baseline process. And as mentioned, you will find the information and also the application form on our website. And yeah, with this, there's only to refer further to the next seminar again. And yeah, I thank you for listening, and I'm open for any questions.